All right, so here we go again. We will be talking about gases primarily today and how energy interacts with those different gases. This is going to be from looks like chapter 13, ideal gas law, heat and heat transfer. But we want to look at the details of this, some of the, or not the details, we want to look at the fundamental aspects of it. Like some of the features of it, the fact that things expand and stuff like that is not as interesting as what's going on kind of deep inside. So let us get started. All right, when you have a substance, that substance is going to be made of different materials, different kind of particles that compose that substance. Those particles are going to have some relationship to each other. What those relationships are depends upon the temperature. So basically what's going on is you have here's two particles of whatever that substance happens to be. It could be a pure substance, it could be a mixture of things, and these objects are going to want to interact with each other. They're going to want to stick together. So there's going to be some kind of bond that is trying to form between them. However, that bond is going to have some energy associated with it. It's not like things just, if there's no energy associated with it, then there's nothing to keep them stuck together, right? They'll come together, they'll just slide off of each other or bounce off of each other. And so if these things come together and they want to stick together, then there's going to be some energy associated with that stickiness, associated with that bond. Basically, the idea is there's going to be some, this is all interactions with the electromagnetic field because these are all electrons that are out. Here's the nucleus and you have these electrons out there. Those electrons are going to be occupying whatever the combined quantum states are. And it's those bonds that bring things together. So it's an electromagnetic interaction. The scale of the charge on a single particle for the most part. Okay, so it's electron bonds in these objects. And what that's going to look like in terms of a potential is you're going to have some kind of thing that looks like this, where actually it's not going to look like that. It's going to look more like this. Okay, where you can't get them too close together, so it goes up to infinity. There's an infinite force because the slope is super duper steep here, which means that there's going to be a huge force that prevents, like you have this object that wants to come over here and bind. If it tries to get, this is a, let me redraw this one more time. Okay, it's going to look like this. Okay, and so this is the position relative to some location, some radius. That radius is going to be determined by where the nearby atom happens to be. So here's this radius. That's kind of the bonding radius where this thing's going to like to bind. So you bring some other particle in this direction, some other particle along here, and it will experience this potential. That potential is set up by the neighboring atom. Okay, so there's going to be a fairly weak force. It's going to be a weak, slightly attractive force out here. And as you get closer, then you're going to get a stronger attractive force, because remember that the force that's exerted on something is proportional to the slope of the potential at that location. So there's going to be force that kind of drives things in towards the center here, and then you're going to get a very, very strong force right here that repels it from that location. That basically just means that you can't take these things and push them together and have them get infinitesimally close to each other. Instead, there's going to be some equilibrium location right here that's going to give you the bond length. Now so this would correspond to this separation here, that separation between the two things. That's going to be the typical atomic spacing that you get in whatever system this is that we're talking about. So if we're talking about a solid, it will be the typical spacing between the sodium and the chlorine atoms, or whatever the case may be. Okay, and things are going to slosh around in here as they kind of bounce back and forth between this. But there's going to be a very strong force that keeps them from coming completely together. There's going to be a relatively weak force. You can pull them apart with relative ease compared to pushing them together. And that's given by, again, the slope of the potential at these different locations. Okay, so now what? Well, there's going to be some energy associated with that bond. That energy is going to be basically how deep in this potential well are you located, because typically you'll measure these potentials relative to a 0 point. You'll fix your origin because you get to choose your origin when you're talking about a potential energy. You'll typically fix the origin as the asymptotic behavior as this goes out to infinity. So you go out to infinity when these things are not interacting with each other at all, and that's 0. And then as you bring them close together, then the bond forms. They experience that force that brings them together. So there's this energy right here associated with that bond. Okay, so now you have all these particles that are in this soup, in this mixture or in this, you have your substance with these particles, and these particles are moving around. They're either moving through space or oscillating, or there's random motions of these particles. Those random motions are going to be related to the temperature. So that, because the temperature is a statement about the kinetic energy of the individual particles in the system. So here you have these things, they're bouncing around, bumping into each other at some temperature, which corresponds to some velocity. It corresponds to the square of the velocity, because kinetic energy is the square of the velocity, and temperature is proportional to the energy. And so temperature is proportional to the square of the velocity of the individual components. And so if the typical energy that one of these particles has is greater than the binding energy that it would have, then you don't have a solid anymore. All right, that's the transition from a solid to a gas or some kind of fluid. So once the temperature is, meaning the kinetic energy of the individual particles, is greater than the binding energy that these particles would have with each other, then you're in a fluid state where things can move past each other. However, as you cool the temperature down, the velocity goes down, the kinetic energy of these individual particles goes down, and once that kinetic energy becomes less than this binding energy, then you will bind things into a solid. So that is how you form a solid. All these particles, they would like to bind together in some way. So you bring them into the same vicinity, but the only way for them to bind together is if their collision energy, which is their kinetic energy, is smaller than the energy that binds them. So if the collision energy is larger than the energy that binds them, then they'll bounce off of each other. If the collision energy is smaller than the energy that binds them, then they'll come and they'll stick together. And that's a phase transition. Okay, the phase transition is once you cross there's some energy associated with the bonds. Once you lower the ambient temperature, or the average kinetic energy of each of the individual particles, once you lower that down to below the energy of the bond, then you go through a phase transition. This is true regardless of what you're talking about. I mean, like, it doesn't have to be chemicals in this case, and it doesn't have to be electromagnetic bonds. So a good example of that is in the very, very, very early universe, there is a thing that's called the Qcd phase transition. Qcd phase transition. Phase transition. The Qcd phase transition, so Qcd is the strong nuclear force. It's quantum chromodynamics, which is studying how gluons interact with quarks. Early in the universe, the bonds that would form things together were, at a given energy. The bonds that form the nuclei, or that form the protons and the neutrons. So I guess I should say what that is. So here's a proton. The proton is made up of 3 quarks. Those 3 quarks are bound together with gluons. So there's this gluon field that's around here. When the universe was super hot and really dense, then these things would, you wouldn't be able to form a nuclei. You wouldn't be able to form a particle. You wouldn't be able to form a proton or a neutron, because you had what was referred to as a quark-gluon plasma. So basically, these quarks were out here. They were interacting with these gluons, and the collisions were so violent that you would never form a particle. If you ever tried to form a proton like this, the next collision would knock one of these gluons out, or would associate with a different object. So you just have this plasma. A plasma is a charge neutral. So in this case, it's the color charge. It's a charge neutral fluid where the force carriers, so the gluons in this case, and the charge carriers, which would be the quarks, they are not bound into bound objects. They're not stuck together. They're free to move around, but if you take any piece of volume, then there's no excess charge. So a similar, when we think of a plasma, for example, a bolt of lightning is also a plasma, except that's an electromagnetic plasma. Electromagnetic plasma, you would have these, the charge carriers, so you have these electrons and the protons that are unbound from each other. So they're not bound together into atoms. So the electrons and protons are able to move around freely, and the force carriers, so the photons, are able to are also stuck in here. So you have this plasma that is photons and electrically charged particles. Any piece of volume, like volume of any given size, is going to be electrically neutral. So you're going to have equal numbers of protons and electrons in there, but the electrons are not bound to individual protons. They haven't paired off. So it's like a big mosh pit. So you have a big mosh pit. Everyone is dancing with themselves, or moving around from one person to the other. And there's lots of energy in the room. And then you cool the system down. You play slower music, and then people pair off to form neutral particles. That would be a phase transition. That phase transition corresponds to what is the binding energy between these charged particles and what's the ambient energy. So if the binding energy between the charged particles is very big, then it takes a huge temperature to have them separate from each other. And then you have to lower the temperature down until they combine together. So, and that works with the electromagnetic force. It also works with the strong nuclear force. So in the early universe, you had this quark gluon plasma where you have the color charged quarks and you have the gluons that are bouncing around, but they're not bound into particles. And then as the universe cooled and spread apart, became less dense, then the quarks would bind into these triples that would form the protons and the neutrons. So that's the very early universe. This is like within the first, I mean, it's before Big Bang nucleosynthesis. So we're looking at like, it's way before Big Bang nucleosynthesis. So we're talking like 1/1,000,000th of a second after the Big Bang. So we can see what this looks like. For example, we experiment on quark gluon plasma at a place called the Relativistic Heavy Ion Collider. So if we go to Long Island, New York, remember the analogy. Yes, the mosh pit. When the mosh pit is happening, the energy is very high. People are just like, jumping around, bumping into whoever they want. But then as the energy cools down and they play the slow ballad songs, then people pair off. And as long as the energy of the thing is, as long as the energy of the music is low enough that the bonds can form, then you'll get people dancing with each other. Okay, so here's Long Island, New York. And if you come up to this area of Long Island, New York, there is Brookhaven State Park, and there's Upton, and there's other things in this area, including the Relativistic Heavy Ion Collider. So that should be right there. This is the Relativistic Heavy Ion Collider. It is a ring right here. So it's similar to the ring at Fermilab, the particle colliders there, except that at Fermilab and at the Large Hadron Collider, they're colliding protons and, well, at the Large Hadron Collider, they're colliding protons with protons. So it's a proton-proton beam. You have two beams of protons that are moving in opposite directions. At Fermilab, it was a proton-antiproton beam. So they had they had protons going in one direction in a loop and the antiprotons going in the opposite direction in the same loop. Okay, so this is a little bit of background information about if you look at the magnets that steer the beams at Fermilab, so they're sending particles, they're smashing these particles together to this atom smashing device. The bore of the magnet at Fermilab is kind of a square bore, but it's a single bore, and they have protons going in one direction and they have antiprotons that are opposite charge going in the opposite direction. The Large Hadron Collider, so this is the Tevatron. The Large Hadron Collider is a proton-proton beam. So they have protons going in one direction and protons going in the opposite direction. And so their magnets look like this. Their magnets have two bores so that the magnetic field is pointed upwards in one of the bores and it is pointed downwards in the other bore, so that the two proton beams go in opposite directions. And then what happens is when they're going to have a collision, they steer these two beams into each other so that they'll collide in their detector. The Relativistic Heavy Ion Collider is this circular beam where they have, instead of putting in protons or antiprotons into this, they have ions. So they have like lead or gold or something like that. And they send those around in this large particle collider, and that looks like this. So they take these particles, they accelerate them to wicked high. Now these are these are atoms. So they're not individual particles, they're like collections of protons and neutrons in atoms, and they send them around wicked fast, and then they smash them into each other, which raises the temperature and the density to recreate the conditions in the early universe. And then they look at, okay, how did this behave? How did the quarks and the gluons behave under the conditions in the early universe? So they have it go through this phase transition. And so if you look at relativistic heavy ion collider, quark. Well, let's look at a collision event so we can see what that looks like. So there's a question: how do they generate the antiprotons at Fermilab? So there is a, what do they do? So it's been a while since I've recreated this, but they have a beam of particles that come in and it hits a target. So they have a bottle of hydrogen gas. That hydrogen gas gets kind of ionized and they accelerate it along a line. And then I think that they peel off some of those hydrogen gas atoms and smash them into a target. That target produces a whole bunch of particles coming out the back end. So they have a kind of low energy collisions, but it's enough to produce a whole shower of particles and antiparticles coming out the back end, some fraction of which are going to be protons. You can select the protons by having a magnetic field and a certain curvature in the area, and only particles with a given mass will escape. And the rest of them, if the mass is too big, then they'll smash into the one wall, and if the mass is too small, then they'll smash into the other wall. And so you can tune the magnets so that only protons will be able to survive, or only antiprotons will be able to survive as you come out. So they send in a particle beam, hit another target, produce a bunch of particles and antiparticles coming out the back of the target, and then they select down to the antiprotons that they want, and then they store them in they boost them up in a booster ring, and then they inject it in to the main ring. So one of these days I should do a whole spiel on how the Tevatron worked, for example. Okay, so this is what a collision looks like in the relativistic heavy ion collider. So it's pretty, let's see, open image in a new tab. So they have these collisions, they come in, smash, and then all this stuff flies apart, and they track all the particles that come out of that. And then they run these tracks backwards to recreate the collision itself. So they're like, oh, here's a whole bunch of particles that came out. They have these different charges, they have these different masses. They know what the charge and mass are based upon how much they curve in the magnetic field. So here's the detector. The beam is going into the bore, and then they have their detector around it. That detector has its own magnetic field that causes charged particles to curve in that magnetic field. And so by looking at the curvature of the different tracks, they can get the mass of those tracks. So then they run the clock, or they reconstruct those paths backwards to the beam line, and they can measure the collision. So basically what will happen is you get a collision, you'll have a particle here, track there, and you'll have another particle track here, and the center of the beam is like this. They don't have detectors at the center of the beam because otherwise the beam wouldn't make it through. Their detector volume begins at some location. So they run these things backwards, and they can say, oh, this is a collision that took place here, and they can tell that it happened at some offset relative to the center of the beam. And so they have all these tracks, and they can reconstruct like what were the collisions that took place and what were the masses involved and so forth. This is also one of the ways that you can measure, for example, the mass of the particles that come out of a collision. So like when the W and the Z were discovered at Fermilab, you would have a collision. It would create a decay. So you have this particle here, it's going to create a decay. It creates a decay by emitting a W or a Z, and then that W and Z decays into like a muon and some neutrino or something like this. And they can see the difference between where this particle was created and where these particles were created, and they can measure that distance. And that distance is tiny. So it's like, this is where the particle was. It emitted a W or Z. So this is the W/Z particle that came out, depending upon what variety of it was. And then they get this decay product that comes out. They track the decay products backwards, and they locate the vertex where this particle decayed. And they also, because of the products that came out from different, the other things that came out of this collision, they know where the center of the collision was. And they can measure this distance, and that distance is tiny. It's like 10 to the minus, it's a small fraction of the size of an atom. So it'd be like 10 to the minus 18 meters or something like that. It's an incredibly small distance where they can measure these things. So relativistic heavy ion collider, this is what it produces. And then what they're looking for is, how do these quarks, like when do you go through the transition where you have particles like protons and neutrons versus a quark gluon plasma where everything is essentially ionized. You ionize the protons and have just gluons and quarks moving around. And so if we look at the phase diagram of a quark gluon plasma. It looketh like this. This is the typical image that is shown. Okay, so hadrons down here. Hadrons are protons and neutrons. So there's protons and neutrons when you have low densities. So here's baryon density is the density of stuff, density of particles. So when you have low densities and low temperatures, you get protons and neutrons. If you have low densities, but you raise the temperature up here, so here's Rick right there, then you can see where this transition happens, where you go from having protons and neutrons, hadrons, to having a quark gluon plasma. So this is the ionization boundary. At low densities and high temperatures, you can get it, or if you go to very high densities, okay, at low temperature but very high density, then you produce neutron stars, where it's also basically a quark gluon plasma. You no longer have protons anymore. It's just a sea of gluons and quarks that are all interacting with each other. So this is the phase diagram of the strong nuclear force, basically, as far as we can tell. So there are different measurements that are made. So the Large Hadron Collider is even lower density. So a gold atom, for example, has more protons in it than a single hydrogen atom, which is basically what the LHC is using. And so you can see these different things. When they get to more massive particles, they're effectively going at a lower temperature. Anyway, so they can map out where this transition is between quarks and gluons and hadrons like this. So these phase transitions, they correspond to something. They correspond to the energy that binds things together. And the same thing is true with things in a solid. So you have a solid. Here is all of your stuff in that solid. All these atoms in the solid are bound together. They have electrical bonds, electromagnetic bonds, or chemical bonds where the electrons are sitting in this thing. And as you increase the temperature, so you're increasing the motion, the random motion of these different particles, then these bonds are going to be strained. The bonds, you have things moving apart, people are going to spread out. As the mosh pit gets too exciting, then people are going to start spreading out because the collisions become increasingly violent between the different atoms in this mix or in this substance. So the bonds will spread out as the temperature goes up. So here is a higher temperature. It's the same substance, but higher temperature, the bonds spread out. And so you get an expansion. So whenever you heat something up, you always get an expansion. That's thermal expansion, comes from that. So here's this substance, you heat up the bonds. Now these things are moving more violently, which is going to spread out the material. The amount of energy that the thing can absorb before it spreads out, so you say, how much energy do these bonds need to, like how much energy do these atoms need to, how much more kinetic energy do you have to add to this system in order to strain these bonds so much more to get some expansion in the bond length? That's the thermal expansion coefficient. For most solids, it's something like 10 to the minus 6. So per degree, per Kelvin, you'll get a 10 to the minus 6 increase in the size of the bonds. So you go up 1 Kelvin, and now instead of the bonds being, let's say that these bonds are, I don't know, like a micron. Well, a micron's not a good example. If these bonds were a meter apart from each other, so that's a pretty big bond, but let's pretend. If these bonds are a meter apart from each other, you raise the temperature by 1 Kelvin, then you will get, the bonds will expand by 1/1,000,000th of a meter, 1 micron. So you have a 1 meter bond, you have these two particles that are out here, a meter apart from each other, they're bonded together, and there's nothing else in between them. And then you increase the temperature, so you increase the amount that they're moving, and the average position separation will be 1 micron bigger for every Kelvin that you increase the temperature. That's basically what's going on here. Of course, that's kind of hard to measure. The only way to really measure something like that is to have a chunk, like in order to measure the actual bond size, is you take a chunk of that material and then you raise the temperature and watch the whole chunk of that material expand. So this is why things expand when you heat them up. Everything expands when you heat them up. There's nothing that contracts when you heat it up. But you may, I know what you're thinking. You're thinking, yeah, but shrink wrap, that contracts. What's wrong with you? And I'll tell you why, what happens with shrink wrap, because it's interesting. So with shrink wrap, what you've got are polymers. So you have these long chains. So you've got these hydrocarbon chains or whatever, you know, that are like this. So it's a whole bunch of bonds that are like this. What they did when they made the shrink wrap is they took this substance, it was like some sheet, and they heat it up. So all these polymers, they get kind of loose, and then they stretch it. They stretch it out. And so all the polymers are pulled into strands. So you have all these long polymers that are pulled into strands. Now their natural habitat, or their natural state, is not to be pulled into strands. Naturally, these things would like to kind of curl up, right? Because they're just like, I don't know, spaghetti. They're like spaghetti. So they would naturally like to form, except it's springy spaghetti, so that doesn't really work. But we can pretend. Their natural state would be to be kind of coiled up. There's some kind of bent, springy stuff. But you heat them up, you loosen up these bonds so that you can manipulate them. They're more malleable. And then you stretch it out, and then you freeze them in place. So that substance is cooled off by basically stopping. You heat it up, stretch it out, and then you turn off the heat source, and then they freeze in place. And then you sell this in a roll. So here's this big roll of shrink wrap material. And then what you do is you put whatever substance you have in there, you wrap it up, and then you take a heating gun and you heat up that material again. So now all these things that are frozen in their elongated form, you heat them up again, which allows them to contract again. It allows them to coil back up again into what they would prefer, their natural state. So as you heat it up, these things loosen up and they start to coil. And as they coil, the whole material starts to shrink. And then it tightens up around your substance. That's not because the bonds are getting closer together as you heat it up. It's because you've taken something and then you've stretched it out and frozen it in place, and now you're relieving that stress by heating it up and letting the bonds become more flexible and pulling it back together. So that is shrink wrap. And so that is, everything expands when you heat it up, because you're talking about actual motions of individual particles that are bouncing into each other. And as a consequence, the more violently they bounce, the larger the recoil will be, and the larger the bond gap or the size of the bonds will be between them in a given substance. So there you go. That's thermal expansion in all of its power and glory. What eventually will happen is, so you have all these bonds like this. Here they are. Eventually what will happen is the energy will get high enough to where you will break one of these bonds. So here's a bond here, here's a bond here. This thing is oscillating around like crazy. Eventually the energy will be high enough that you'll break one of these bonds, and then this object will come flying off, and it's like, I'm free. So here it is, the free particle. It is now very happy that it's free. So there's a smiling face. Now this particle is free, and what's going on here? So you had a solid. The bonds are being strained by the vibrations of this solid. You break one of those bonds, you know, for some reason, like you have a sound wave that's propagating along this direction, another sound wave that's propagating along this direction. They impart some energy to the neighboring particles because, you know, that's what sound waves do. They transfer energy from one place to another. And then this one happens to be at the apex where both of these sound waves collide, and so it's got slightly excess energy. It's got a little bit more energy than the average. So all these bonds are going to have, or every particle is going to have some amount of energy. They're not all going to be equal to the average. There's going to be a distribution of energy around the average. So some of those particles are going to have more energy than average. And if that more energy than average is sufficient, it will break the bonds. It will release this particle. Now it's free to fly through space, all through space by itself, or through the atmosphere by itself. Okay, so what just happened here? You had extra energy. There's some amount of energy in this solid. You've now removed the most energetic particle. You've concentrated that energy in a given location. You've removed the most energetic particle from that substance. Okay, what does that mean? Well, now let's say that you had a little bit of energy to begin with. You had some here, and you're kicking a small amount of that energy out. So, you know, some little bit of energy that gets kicked out. That means that what's left over, because energy is conserved as long as the second is the same length of time from one day to the next, which it is, then this energy has to be conserved, and so the remaining energy has to go down. So the remaining energy drops to E minus the little bit of E that's lost. Okay, so now what do you have to do? Well, if you want to continue ripping these particles, liberating these particles, you're liberating these particles from this substance, then you have to add energy to the system. So you have to have a burner or something down here that you're adding more energy to that system in order to break the next bond. Because every time you break a bond, you're removing some energy, which is going to cool down the remainder. So you remove energy, now the rest of it's going to be colder because it's got less energy. So you have to add more energy to the system through some mechanism. So it could be a flame. This is a flame, by the way, even though it doesn't really look like a flame, this is a flame. You add more energy to the system. Now you're increasing the kinetic energy of individual particles. You're going to strip another one out or liberate another one. And then as it's liberated, the energy of the remaining material is going to be dropped back down again. And then you're going to add more stuff. You're going to liberate another one. So it's like, this is Cuba, right? Here's Cuba, and we're liberating all the people out of it but you do it by adding heat to the system. So every time something leaves, you lose energy, and then you have to recover that energy. So there's a total amount of energy. If you have a big chunk of this substance, there's a total amount of energy that you have to add in order to break all of these individual bonds. So you have Avogadro's number worth of bonds. Each one of those bonds has a certain amount of energy associated with it. You have to add that much energy in order to break all those bonds, and that is called the latent heat. Latent heat. Latent heat is the energy that it takes to go through a phase transition. And the reason it takes so much energy to go through a phase transition is the very process of going through the phase transition tries to undo itself. So you've raised the temperature, now you've liberated some particle, and the temperature of the remaining particles goes down. And so you have to keep adding stuff to the system. You have to add a certain amount of energy in order to boil the whole substance away, or to melt the whole ice cube, whatever the case may be. The very process of melting it undoes the heating. Undoes, that's a great word. It undoes it. It undoes the heating process, right? It cools it off. Going through the phase transition cools you off. And so in order to complete the phase transition, you have to keep adding heat to it. So that is something to remember. That's why there's this latent heat of fusion and the latent heat of vaporization, is that while raising the temperature of something, as you add energy to the system, the particles start moving faster. The amount of energy that it takes to get them moving faster by some amount is called the heat capacity. How much heat can it absorb before it changes its temperature? So the heat capacity is how much does it cost? How much energy does it cost to increase the speed of the particles in the bonds? And if the bonds are more stiff, then it's going to have a higher heat capacity. If the bonds are more floppy, then it's going to have a lower heat capacity. And then in order to go through the phase transition, now you're actually the process of evaporating it is going to attempt to cool the system back down. So you have to keep adding the heat at the phase transition. This is also why phase transitions happen at a fixed temperature. So you raise the water up to the boiling point, and it will stay at the boiling point as the water evaporates until all the water is evaporated, and then you can continue to increase the temperature of the steam. And so you halt, when you go through the phase transition, you halt at a given temperature, because that's the temperature that corresponds to liberating all of these bonds. But the process of going through the phase transition cools it down, and so you're basically fluctuating incredibly rapidly at the phase transition temperature. So there you go. That is the different phase transitions. And everything goes through these different phase transitions. It all depends upon, basically, what is the energy of the bonds. So you have some energy, and that corresponds to the bonds in this system. So again, this was the potential. So you have things sitting down here. You need to come up to this amount of energy in order to free those particles. And so once you reach that temperature, then you go through this phase transition. Or if you're going the other way, if you're cooling the temperature down, once the energy of the particles is less than the binding energy, then you will start to form the bonds that will create your more condensed phase. So, and it doesn't matter, it could be the electromagnetic force that produces these bonds, it could be the gravitational force that produces the bonds. So you have two objects that are interacting with gravity, they're going to have some binding energy. If you have a series of stars that are all orbiting around each other, like you have a globular cluster of stars, those stars are going to be bound together through gravity. And if you have if you add energy to the system through some mechanism, then the stars are going to start orbiting more rapidly. How would you add energy? I mean, gravity is kind of hard to, kind of a weak force to be adding energy to the system, but it can happen. So you could, for example, you could take a collection of stars and pass them through another galaxy. So you have another source of gravitational energy that you're adding to the system. That's going to cause the stars to oscillate or to orbit around more rapidly, and they will be stripped out. Like the most energetic ones will be kicked out of the star cluster, and the remaining material will fall further deeper into the star cluster. So with gravitational force, you can ionize things. So for example, if you have, we know of planetary systems where planets get ejected out of those systems because we've seen the ejected planets. They're called rogue planets. They're completely ejected out of the system. So there's no star that they orbit. They're just planets that are drifting through space all by themselves. So it's basically ionization, except instead of the electromagnetic force and ionizing through the electromagnetic force, it's the gravitational force that's binding them together, and you're ionizing them through the gravitational force. The same thing happens with the Cork gluon plasma, where you go through the same phase transition. It's a different force, different particles are being exchanged, gluons in that case, and different force that's interacting. In that case, it's the strong nuclear force instead of the electromagnetic force or the gravitational force. Okay, so there's that. What were we talking about? Let's see what we've covered so far. We did temperature, we did heat capacity. So heat capacity is how much energy do you have to add to the bonds in order to get these things to oscillate more rapidly. The tighter the bonds, the harder it is to get them to move, and so the higher the heat capacity is. So we talked about phase changes. So now we can move on to what happens when you make a gas. So one of the things we talked about last time was the equation of state. Talked about the equation. This says equation, E-Q-U-A-T-I-O-N, equation of state. And the equation of state is the relationship between the pressure of something and the density. So the pressure is some function, or it's probably best to do it the other way, that the density is some function of the pressure. Or it's the relationship between the density and pressure. That's the main thing. Okay, so as you increase the pressure on some fluid, the first set of chapters on thermodynamics and fluids was, let's assume that it's incompressible, which means that the density is a constant. It's a function of the pressure, and it's constant. So it doesn't actually depend upon the pressure. No matter how much the pressure is, the density of the fluid is going to be constant. The truth is that nothing behaves this way. It's just that many substances, it's a very, very, very weak function of pressure. So if you were to plot, for example, the density as a function of pressure for water or something like that, it would look like, let's see, so as the pressure goes up, the density is going to go down. As the pressure goes up, the density is going to go up. It would look like this. Okay, it's got a tiny, tiny rise in the density as the pressure goes up. And so you say, well, this is essentially constant, so let's treat it as a constant. That's fluids from the previous chapters. The fact of the matter is that all substances, when you increase the pressure, the density will be affected as you increase the pressure. It doesn't always go in one direction. So you can have substances where if you were to plot the density as a function of pressure, is pressure the right way to do this? Okay, so let me change this. Okay, anyway, so I'll 1 second. Density is a function of pressure. In general, it will be that as you increase the pressure, the density will increase as well. Okay, you might go through a phase transition where you have some crystal structure that's more stiff, so you have a density versus pressure like this, and then all of a sudden it jumps, and the density goes up very rapidly or more slowly as the pressure increases. Another way to describe kind of the same type of stuff is to look at the density as a function of temperature. And this is where I was, where my slight distraction came from. You can look at the density of something as a function of temperature. So for example, you could look at the density of ice as a function of temperature. as you lower the temperature at the same pressure, what happens is the density goes down and then it goes back up again. So the maximum density, let's see, I meant to say that it goes like this. So water follows this type of curve, where as the temperature goes up, the density goes down, right? So as the temperature goes up, the collisions become more violent and things spread apart, so the density should go down. And as you lower the temperature, things get closer and closer together, and then you're approaching the phase transition. So this region here, as you approach the phase transition, the water molecules are trying to find a structure that they can form, like they want to form a solid, but these water molecules are big floppy, well, they're not big and floppy, they're not like hydrocarbon chains, but they're these, Mickey Mouse shaped things. They're weird shaped objects. And so as the substance is trying to form a solid, the bonds get, they get closer together. They're trying to arrange themselves into a regular pattern, which means that they can't have any orientation. They can't just be wedged in next to each other. And so ice will actually, as it approaches that phase transition, in lowering the temperature, it will rearrange itself and it will actually spread the bonds apart. And so ice floats on water because as you get close to the freezing point, the water molecules are going to rearrange themselves so that they can form this regular crystal lattice, however they want to bond with each other. And in doing that, the water molecules are going to spread apart slightly by 10%, right? Well, 10% by volume. And so by the time you actually freeze the material, the water is floating on the top. We should all be grateful. Everyone should be grateful that water expands slightly as it goes into the freezing phase transition, as it transitions from a liquid to a solid. Because if water didn't expand as it went through that transition, we'd all be dead. The oceans would freeze from the bottom up, and there would be no way to melt the ice because the energy from the sun can't get that low, and so everything would be frozen over. But because ice floats on the surface, it's easier to melt, and on the surface of the water, it's easier to melt, and so the oceans stay unfrozen. So dodged a bullet with that one. Anyway, so that's temperature and pressure. This is also, these are also related through the equation of state. So the density as a function of pressure, the density as a function of temperature, the equation of state basically relates all of these quantities. So for a solid, you'll get many fluids and many solids. It's relatively flat. The equation of state is relatively flat. The density basically stays fairly constant, although it's not constant. It does have some slope to it as you increase the pressure. Gases, on the other hand, are easy to squish around. Like you take a tube of gas and you put it in a bicycle pump, and you can, with your puny arms, you can get it to change its volume. And so changing the density of a gas is very easy. And so you look at, okay, what's the relationship? What is the equation of state that relates the density to the pressure and the temperature for a gas instead of for a solid? Okay, if you have an ideal gas, one that behaves exactly the way that you think it should, then what you get is that the pressure is equal to the density times kT, where this is Boltzmann constant right here. Okay, so, and the density is the number of elements per unit volume, so it's the number of atoms per unit volume, and this gets you, well, it's the number of atoms, and so it's going to be a capital N, and so that gets you, if you rearrange this, then you get PV equals NKT. So the ideal gas law is the equation of state. It's the relationship between density and pressure and temperature for that particular substance. Most gases are not perfectly ideal, but this is, close enough. Well, it depends on what it is that you're doing. It can be close enough if the error that it introduces by having a non-ideal gas is less than the tolerance that you have for your system, whatever that might be. Any other liquid that behaves like water? In the case of like the things rearranging themselves, I would suspect, I'm sure that there are, I suspect that it is any substance where the molecule is asymmetric. So the water looks like this. Okay, so it's not symmetric, where if you had ammonia looks like that, where it is symmetric. And so my suspicion is, I don't know this for sure, but I would be surprised if ammonia increases its density as it freezes. It's possible, but I suspect not. Where water, because it's an asymmetric molecule, you can squish it together in, you can have it arranged in kind of weird shapes, in the liquid form, but if you want to form a regular crystal lattice out of it, then it's going to have to, the bonds are going to have to be between the hydrogen atoms in a certain way. And so it's going to arrange itself into a crystal structure, which is not necessarily going to be the most compact structure that you can form. Okay, so the ideal gas law, this PV equals nRT or PV equals nKT, that is the equation of state. It relates density and pressure. All right, so that's the ideal gas law. That is an equation of state. Let's see, did this, phase changes. Okay, so there's a good question. So how is this not symmetrical? So the question is, how is this not symmetrical? Because it is symmetrical relative to that axis. That's true. So water molecules are symmetrical relative to the axis or a plane that cuts through them from one side to the other, but it's not symmetrical to this plane. Where if you have ammonia, if you look at the center of mass, so that's another way to look at it, is where's the center of mass? So the center of mass in the hydrogen atom is not in the center of the oxygen molecule. It's displaced away from the center of the oxygen molecule. The center of mass of the ammonia atom is directly in the center of the nitrogen that's here. And the same thing with methane. Methane would be CH4, and it would have a form like a tetrahedron. And the center of mass of CH4 is going to also be at the center of the wait, is that true? It has to be. It has to be at the center of the is that true? I don't see how it could not be, because how do you know which one is up? If it's all the same in every direction, how do you know which one is up? There's no up, right? This thing looks the same, magically the same as this thing if you rotated it 120 degrees. And so that implies that the center of mass has to be at the center of the atom. So ammonia is it's not polar. It really comes down to whether it's a polar atom or not. Symmetrical probably depends on how you're defining your symmetry. So geometrically symmetric is probably not the best description to use. Rather, it's probably better for me to say that it is a polar atom, which means that, okay, here's your hydrogen atoms, here's your oxygen atom. The hydrogen atoms are going to share their electrons with the oxygen. And so the electrical charge, you're going to have a net positive charge up here, and you're going to have a net negative charge over here. Because while an individual hydrogen atom is neutral, it's going to be sharing its electron with something that is in a particular direction. And so the electron is going to be spend some fraction of its time around the oxygen atom. So the charge distribution is going to be more centered on the oxygen atom, which is going to mean that there's going to be more electron cloudiness down here and more proton, like bare proton up here, which gives you a polar molecule. Where with ammonia and methane, this doesn't happen. So ammonia is more symmetrical than water is. Water has one axis of symmetry. Ammonia has 3 axes of symmetry. And methane has 4 axes of symmetry. Okay. So when you have an asymmetric atom, then I could imagine that would be where the thing that's actually driving the expansion as you cool it down. All right, let's see. So we have an ideal gas. There are a few things that we need to consider with this ideal gas. So we have this ideal gas law that is the equation of state that relates the pressure and the density and the temperature. So let's pretend that Boltzmann's constant is equal to 1. We're going to work in some units where Boltzmann's constant is equal to 1. Instead of SI units, it'll be something else. So that means that pressure squiggles the density times the temperature. So if you, what's a better way to do this? Well, this says what? If you increase the temperature at a fixed density, so the density is fixed, and you increase the temperature, then that means that the pressure has to go up. So you have a container, like this. It is filled with a gas, an ideal gas in this case. It's filled with a gas. You add a bunch of energy to the system by having the fires of enfer down here absorbing energy into the system. So the temperature of the gas goes up. What's going to happen? Well, you're going to build up pressure in that system. So the walls are going to be filled, like the walls are going to feel the strain as the increasing violence of the particles bumping into the sides. The density can't change, right? Because it's a fixed amount of gas in a closed container. So the density, it's not possible for the density to change. So as you increase the temperature, it's going to increase the pressure. Okay, let's see what else happens. Let's suppose that we keep the pressure constant. So the pressure stays fixed, but now you can change the density. So that would not be this case. Having pressure constant would be like having it in the atmosphere. So here's a chunk of atmosphere. You've got an ambient atmospheric pressure, and you're considering, some volume with, in some kind of massless container that's able to expand and contract, like a balloon, except without the elastic properties. So then what's going to happen? So the ambient pressure is fixed. So this is constant. In this case, the pressure is constant, but you increase the temperature. So what's going to happen to this gas as you increase the temperature? So if the pressure is constant and the temperature goes up, then that implies that the density has to go down. So that means that in order for the density to go down, the volume has to expand. So this substance is going to expand outwards like this. So that's how the equation of state works. So now you have, how useful is it? Why would we care to know like how gases behave, or even solids for that matter? Well, one thing is we build buildings out of solids, and so it's kind of important to know how things expand. We can see what happens if you don't account for expansion of things. We can look at thermal expansion roads, pictures of what happens to so it's about $1 million per mile to build a road. And this is what happens if you don't account for thermal expansion. You get cracks and the road buckles like that. And it's a huge buckling. And so to prevent this from happening, to prevent the road from buckling as the road expands, you add expansion joints. And this is especially important on bridges, because bridges are floating up in the air. And so if you're going to sit there and expand and contract and expand and contract and weaken all of the cement, because cement isn't very good at, like cement, you can compress it, but you can't pull it apart. You can compress cement and it will retain its integrity. You can't pull it apart and have it retain its integrity. It's like it crumbles as it pulls apart. So if you have this bridge and it's expanding and contracting all the time, then the cement's going to crumble, and then the bridge will fall, and then people die. And we don't want people to die. So instead we add these joints so that the bridge can thermally expand and contract without crumbling and falling into the chasm below. So that is, that's why these things exist when you drive over them, the expansion joints. Buildings will have expansion joints. So in the building that I that I work in, there's an expansion joint in the ground. And so as the temperature, because the temperature does get pretty warm in Las Vegas, as the building expands because of thermal expansion, there's a joint in the building that allows for that to happen without compromising the integrity of the concrete. So let's see. So these thermal expansion joints are important. Just to give you an idea of how important these things are, like how much something will buckle. This is a question that I often have my students answer, and that is, let's consider, just briefly, let's consider a bridge that is 200 meters. So you have a single bridge that's 200 meters across. Okay, and let's say that you have a 10 Kelvin expansion. So the temperature is going to rise by 10 Kelvin. And you have a thermal expansion coefficient. So how much this thing is going to grow is going to be... this is all coming back to, like, why do we care about the properties of materials? And the answer is that it actually matters. It costs energy to repair these things. And energy, you spend your money to get energy. And it takes energy to repair things. And so you're spending your money when you could be devoting it to other things like watching Twitch. Okay, so you have a 10 Kelvin expansion, and let's say that you have like 10 to the minus 6 expansion coefficient. So you cut this in half, you expand the thing, and let's pretend that it's going to buckle into an isosceles triangle. You'll see why I chose these numbers here in a minute. So it's going to buckle into an isosceles triangle like this. question is, how high is this going to be? So there's H. All right, so this is going to be 100 meters. You have a thermal expansion coefficient 10 to the minus 6, and you're raising it 10 Kelvin. So that means that you're going up to 10 to the minus 5. Okay, so this length here, that's 100 meters. This H, and so we have 100 meters squared plus H squared is equal to the hypotenuse, and the hypotenuse is the expanded distance. So the hypotenuse is 100 plus 10 to the minus 6 times 10, 10 to the minus 5 squared. Okay? So it's 100 meters long. Wait, hold on. It's 100 meters times, I did this wrong. It's 100 meters times 1 plus 10 to the minus 5, because it's 10 to the minus 6 per Kelvin. We went up 10 Kelvin. And then this whole thing is squared. That's what this is. Okay, so I should be able to do this. So H is equal to the square root of a whole bunch of stuff. The 100 squares drop out. I'm going to get, right, if I multiply this out, if I FOIL it out, then I'm going to get 100 squared. That's going to cancel both sides, and I'm going to get a plus 2 times 100. So that's 200 times 10 to the minus 5. So I'm going to get 200 times 10 to the minus 5, and I'm going to have the square root of that. And then there's going to be this thing that's 10 to the minus 10, and that's going to be negligible. All right, if I FOIL this thing out, then I get 200 times 10 to the minus 5. All right, what's the square root of 200 times 10 to the minus 5? That's 200. I can do this probably using a calculator. I'm going to say square root of 200 times 10 to the minus 5 is 0.002. And I get 4 centimeters. So 100 meters long with only 10 degrees. That's like day-night fluctuations. You get 5 centimeters of buckling. So that's quite a bit. If you go to 100 degrees, and if I put in more realistic numbers, then you're looking at like a meter of deflection. So over the course of a given year, from winter, the coldest night in winter, to the hottest day in the summer, you can get things where you would have a whole meter of buckling on a 100-meter bridge because of thermal expansion. If you put in the real numbers, these are just estimates here. So that's pretty gnarly. I think if I go to like this 2 centimeters, then you're looking at quite a bit. Anyways, so thermal expansion, that's why we care about this stuff. That's why we care about ideal gases. Okay, now when we deal with ideal gases, we have a gas. We want to be able to, maybe there's something else we can use that is, where we can use this relationship. Okay, there are other ways that we can use this relationship. One of them is to imagine, for example, how much energy does it take to raise the pressure versus how much energy does it take to expand something. So if you have a pressure cooker, so you have a chamber that's fixed volume, then raising the pressure is simply a matter of raising the temperature, right? PV equals NKT. If I want to I have a fixed volume and I have a fixed number of particles, and so the density is fixed. And if I want to increase the temperature, or as I increase the temperature, then the pressure is going to go up in direct proportion. However, I can imagine having a system where I also have to change the volume, where maybe it's a piston, and that's actually what we're going to be talking about. So here is a piston. Here's your cylinder. You have a piston in it. It looks like this. And now, as I increase the pressure, I can drive this piston upwards. Okay, so then the question is, how much do I have to increase the temperature in order to do this? Well, if you're increasing the temperature, you're going to increase the pressure in this system, and you're also going to expand the volume. So the energy is going to be shared between just increasing the pressure in that cylinder and also expanding the cylinder. You're going to, it takes energy to raise this up against gravity. And so the question becomes, does it take more energy or less to expand the volume? The answer is it takes more. The reason it takes more is because both increasing the pressure and you're increasing the volume. And when you're increasing the volume, you're pushing against the atmospheric pressure. You're expanding this piston against the atmosphere or against the ambient fluid. It might be, underwater or something like that. So the heat capacity, the amount of energy that it takes to raise something by a given temperature, the heat capacity at constant pressure is lower than the heat capacity. Let's see, hold on a second. The heat capacity at constant volume, that's this one. This is the constant volume where the volume is fixed. That heat capacity is lower. It takes less energy to raise the temperature when the volume is fixed. If the volume is free to move, then not only do you have to increase the energy in this substance, but you also have to push against the ambient volume or the ambient pressure. So not only are you increasing the motion here, but you're also pushing against the atmosphere and creating, you're adding energy to the atmosphere by expanding against it. So you have gravitational potential energy of the atmosphere sitting on top of your piston, and as you add energy to the substance, you're going to expand the piston and push away the atmosphere against the force of gravity. And so if the volume is not fixed, so fixed volume is over here, if the volume is not fixed and the pressure instead is fixed, so the ambient pressure, this is going to have a higher heat capacity. It takes more energy to push against the atmosphere and expand the volume. So you have two different ways that you can deposit energy in the system. You're adding a bunch of energy to the system through one way or another. It could be through a fire from underneath that you're absorbing energy to the sides, or it could be from some chemical interaction that you're having take place in there. At fixed volume, you just add the energy to the system. If the pressure is fixed and you can expand the volume, then you're not only adding energy to the system, but you're also pushing the atmosphere away. Okay, and what's going to happen is that you're going to share the energy between those two processes. So if you just add energy to the system where both things can happen, then you're going to get it to partition between the two. And that's going to give you a relationship between how easy is it to add energy at constant pressure compared to how easy is it to add energy at constant volume. And that really boils down to what are the different ways that you can store energy in your gas. So, and here is kind of a weird thing. So let's say that you have a gas that looks like this. Okay, it can have kinetic energy, because remember that the energy that you're adding to the system is going into all forms of energy that are available to you. If you have a gas that's just individual particles, like helium, for example, the only energy that it can have is, not counting gravity, the only energy that it can have in this system is its kinetic energy, its motion in these three different directions. On the other hand, thank you for that raid. I appreciate that, Demon Machine. Hope everybody's doing well. So if, on the other hand, it's a perfect time for Demon Machine's audience to come in, because we're going to be talking about car engines here in a minute. If you have an atom that is diatomic like this, so like say oxygen, O2, or nitrogen, N2, then what's going to happen is not only do you have the kinetic energy that you can deposit it, so you're adding energy to the system by, you have a fire outside and you're driving, you're concentrating that energy through thermal absorption or whatever. Anyways, energy is coming into the system. You can both add energy to the translation of this particle, but you can also add energy to that bond. You can get these things to start shaking and vibrating with respect to each other. You can also get these things to start rotating. Okay, so you can have like this dumbbell type gas molecule spinning on its axis. And so that rotation is another energy sink that you have to contend with. So if you have some big floppy, some gigantic hydrocarbon chain, like it's a piece of coal, like say you vaporize coal or something like that. You have this gigantic hydrocarbon chain and you're adding energy to that system, then not only can you translate this thing around, but you could also just deposit energy into the different vibration modes. Like you can get it to vibrate like a string, you can get it to scrunch in and out, you can set up different kinds of standing waves depending upon how these things move. You can have a whole bunch of different ways that this thing can oscillate, right? It can oscillate like this, it can oscillate like that. You could have the hydrocarbon chain kind of bending like this. You could have the hydrocarbon chain going all the way up to the point where each individual hydrocarbon atom is oscillating opposite its neighbor. Okay, so there's a variety of different ways of storing energy in these long hydrocarbon chains compared to helium, which is a monoatomic gas that can only translate. So the relationship between how much energy do you have to add to the system in order to get the volume to expand. The relationship between the heat capacity at constant pressure and the heat capacity at constant volume depends upon the nature of the gas that you're talking about. Okay, because the heat capacity is how much do I have to add, how much energy do I have to add to raise the temperature, and the temperature is related to the kinetic energy, the motion, the translational motion. So if you have a lot of different ways to store energy in an atom or in a molecule, then not all of that energy is going to go into the translation, right? You have this thing, and you have a half a dozen different ways of storing energy. You have a half a dozen different vibration modes that you can excite. You have a half a dozen ways that it can rotate or spin or something like that. You have all these different ways of storing energy that are not the translation mode. And it's only the translation modes that contribute to the pressure, because that's the pressure is these things slamming into the side of your container. Okay, so that is when you have big floppy molecules, the heat capacity at constant pressure and the heat capacity at constant volume become more and more similar. Is it like entropy? Entropy is a bit different. Entropy is a bit different, but it can contribute to these things because the higher the entropy there is a tendency for things to go to a higher entropy state, but we haven't talked about that. What if the net vibration cancels out? Well, so if there is vibration, then there's no canceling out, right? There's either you add energy to the system or it's not there. So you can't have, you're talking about the individual motions of particles, and you can't have one vibration cancel out another, right? They combine, just adding one thing onto the next. Anyway, so this relationship between the heat capacity at constant pressure and constant volume, that's called the Adiabatic Index. Okay, and it's given by the Greek letter gamma, which is also for photon, because there's only so many letters that we can use. So this is the Adiabatic Index, and it's the relationship, it's the ratio of the heat capacity at constant pressure and the heat capacity at constant volume. So the easier it is to heat up a gas, it's easier to heat up a gas if the gas is small molecules compared to heating up a gas that is big and floppy.